Yeah, so welcome back. This is where we stopped the last session. So yeah, we are proceeding to the stability analysis. This stability analysis actually, what it actually means is to like make sure that your retaining structure does not overturn and does not slide away due to the active, because the active pressure here is the main is the most critical load condition or consideration to say. So this passive action or passive pressure is acting like this, and the passive is trying to resist it. So you I would want you to get familiarized with these terms that I'll be using. This is the disturbing, as I said, active, the disturbing pressure, and this is actually like any pressure that is countering it is the resisting pressure, or the stabilizing, this not destabilizing, the stabilizing pressure or action. So these are our dimensions and parameters. From here to here is the stem bottom depth, and here no is not equal, is 0.3, and the retaining like the wall height, which is from the peak to the bottom, not necessarily to not necessarily to the bottom. So is from here to this point where the soil is being retained is 8.14. Now to this table. This table A, okay, this is the column for the loads, the loads, and these are the vertical, the load types. I mean, then these are the loads themselves. These are the vertical loads, and these are the horizontal load. The vertical loads, of course, are the loads that are acting in the gravity direction, and the horizontal load again are, as it sounds, horizontal. Then these are the distance to or from the toe, the tip of the toe. You are going to be you would understand that subsequently. This is the bending moment. You know, when you multiply force by the perpendicular distance, you get the moment. So now here we have 0.3 meters multiplied by 1 multiplied by 8.14 multiplied by the density of concrete. This 0.3, okay, we are going to divide this stem into like reasonable shapes to make our lives easier. So dividing this would give you a rectangular shape. So we are trying to look for the area. To get the area, the width is 0.3 and the height here is 8.14, which is what we have here. 8.14 multiplied by 0. This one here is like 1 meter strip. Then multiplied by the density, we get 58.61 in kilonewton. Because if we don't multiply it by this one, we are getting it in kilonewton per meter, but we don't want it in a linear term. We are trying to get them in force. Same thing goes with this. We are taking the area of the triangular section here, the triangular section of the stem, and the formula for the area of triangle is half base times height. So half of the base is is 0.5 multiplied by the remaining parts from 500, removing 0 points, right? Sorry, removing 300, we have 200 which is 0.2 meter m. So 0.2 multiplied by the height divided by 2, that's half base times height, then times the 1 meter times 2.24, which is the concrete density. Same here goes with this, the base slab. This is the base slab. Our our base slab here is 6 meters, then the thickness is 0.7 meter. 6 times 0 times 1 times this concrete density would give us 108. Same here, then the backfill soil, which is this, which is the main character we are designing for here, or we are designing against here, is the area of the area of the soil that is being retained, which is this, the height multiplied by the width. And our width is 3 meters, then the height is 8.14. That's how we have it here. 3 multiplied by 8.14 multiplied by 1 meter, then multiplied by the soil density, which is 20 here. We have 488.34. Then the toe soil is, which is just this side, which is the passive in term. The passive soil is also going to be considered, but shouldn't have been considered. You will be understand that later. So the remaining little part is, this is 0.889 minus 0.75. You have about, it's not 0.1 or what? Yes, 0.139. So we have the top projection multiplied by the thickness of that soil area, which is this, multiplied by 1 meter, and the soil density, we have this to be 6.95. That's all for the vertical forces in the retaining wall. Then the horizontal force is actually only one, which is why I said this shouldn't have been considered, but it's all good. We are not considering it in the horizontal force section, because the most critical mode of failure, or the most critical load pattern here, is when the active pressure is acting on it all through, because this might not always be here. So we are only taking into consideration this soil being here, because that's the most critical mode or arrangement. So we have our pressure, which is gotten by Ka times gamma times this is the formula, gamma soil, of course, multiplied by the height, again this height, squared over 2. That's the formula to get your force acting on the stem of the retaining wall. So that will give you 263.1 kilonewton. Of course, multiplying it by 1 meter, because that's just the pressure. This gives you the pressure, but then when you now multiply it by the 1 meter strip, you get it in kilonewton. So this is where another work starts. I'll need to paint some things here. I don't know if I should redraw this. Okay, let's not redraw it. Let me just be explaining. So this, as I said, is the perpendicular distance from where the point, the load point is to the toe. The distance from, let's say, for this stem wall, which is just the rectangular section of this stem wall. So the point load is actually acting on this point here at the center of the stem, and this is where this is our reference point to this point of the toe. So the perpendicular distance is literally half of this height, which is half of 8.14, then plus 0.75 would give us this no, that's for the horizontal force. We are considering vertical forces now. the gravity load or force, sorry. So this point is actually going to extend from here to here. Then this, so how do we get it? It is 2.5 plus is the first 0.2 here, then half of 0.3 would give us 2.85. If we can do that, 2.5 plus 0.5, no, not 0.5, 0.2 from the, this is the stem wall. We have this to be 0.5 and this 0.3. So half of this, no, not half, let's first take this thing, the triangular part. This is 0.2, which is what we got here, what we wrote here. Then plus again half of this place is 0.3. Half of 0.3 is 0.15. 0.15. When we add this, it should be giving us 2.85 meters, that's what we have here. Then similarly, we do the same thing for each and every single section of, let me quickly do for this little triangle here. Okay, so for this triangle, for this triangular section here, we are going to, of course, add from this place to the edge or to the face of the stem wall. Then this one is not so difficult like that, but people tend to find it difficult. I don't know. Okay, let me try it very well. Calling this one 0.3, here to be 0.5. Remember, here is 0.2, which is 200. The load is going to be acting 1.3 from this place, 1.3 from here. It's actually 1.3. This is 1.3. 1.3 of this 200 mm. 1.3 of it, I'm not with calculator, so I'm not going to do it. So this remaining part is actually what we need, which is 2/3, because if this side is 1.3, the other part will be 2.3. 2.3 multiplied by the length of this place is going to give us whatever. I'm not with calculator again. So that's what we did there. I think, yes, it should be 1.33. 1.33, that, and that's what we did there. It is 1.33. Then when you add, when you sum them, it's going to give you 2.63. Then for the base slab, is since it's perfectly rectangular, it's not complicated, and our width is 6 meters. Half of 6 meters, what is it? It's not 3. Yes, it's 3. So 3 meters from here to it is actually 3. So that's how this 3 comes about. Then this 4.6 is actually, you see, from the backfill. The backfill length is 3 meters. Half of 3 meters is half, 1.5. I mean 1.5. Yes, 1.5 is 1.5. So 1.5 plus half, that's 2, plus 2.5, that's 4.5. And that is where 4.5 comes from. Then the toe distance, the soil toe is basically half of this side just to this place. That is how that one is. That's how we got that. So now for the horizontal arm length of the soil, of the active soil, yeah, we are as I wanted to say earlier, this is the area that we need, and this is where actually the concentrated force is and we're actually taking a perpendicular distance from here to this point to the bottom of the retaining wall. We are taking moment about it too. Now, what is the perpendicular distance of this for of the force? It is basically half of this 8.139, half of it plus 0.75. That is how we got whatever is there. I'm not a calculator again to do that. Then this bending moment is simple. You just multiply your your force by the arm length. We get the bending moment. That's our bending moment. Then these are the summation of all the moments. Here we are going to sum all the horizontal forces too and all the vertical forces. Here we call the vertical forces the resisting force, and the horizontal forces the disturbing or the destabilizing force, which is what we again right here. This is the resisting force or the stabilizing force, not the stabilizing force, the stabilizing force. So this is the disturbing force, and yeah, this is the resultant of all the moments. But now there are two moments. There is disturbing moment and there is resisting moment. We are now going to consider only the resisting moment at first. The resisting moment is basically the summation of all the positive moments. Because this one is negative moment, is the bad guy, is the bad air there. It is the one returning it. So the summation, yes, we only have a disturbing moment that which is due to the active soil. We have this to be minus, but we don't need to put any direction there because we already know it's disturbing and it's going to the disturbing direction. It is disturbing the structure, going like this, while this moment is the resultant, no sorry, is the resisting, why this is the resultant. This plus minus this is what we call the resultant. Then getting the eccentricity, we have to divide the resisting moment over the force, the resisting force, which is we have this is our resisting moment and this is our resisting force. We have 2.89, and our breadth is 6 meters. The width of the base slab is 6 meters. Now to now check to check if the eccentricity is within the acceptable limits in a way that the the toe won't be too overburdened by the pressure. This is the deformation. You know, these forces here can only be in compression. It must not be in tension because soil cannot pull. It can only be like it cannot pull again. It can only resist. So you applying force to this toe. I don't know if you I don't even know how to explain this one. Okay, this is the retaining wall. Let's go back. So okay, yes. This is the retaining wall. Yeah. And this side is going to we would want to push this like this. As this one is pushing this like this soil here would be pushing this too like this. Then this one too, the soil, the ground soil would be pushing this. If this is not happening, this is not a retaining wall, this is a mechanism or something else. It means it is not stable. It is actually is an unstable structure. But now we've gotten this eccentricity to be less than b over 6, which is 1 meter, and the eccentricity is okay, which is way below the the allowable permissible, the permissible limits. So we are safe in that the foundation base is okay, which is a toe in this case. Now we are now looking into the heel design, heel and toe design. Heel and toe. Since we've checked the eccentricity to be okay, we are good to go. And going back to the heel and toe design. Yeah, let me okay, yeah, this is the diagram. Before we get there, or let me show the diagram first. As I said, moments. Oh, this is how the moment is going to be. This will be exerting force on this place, and the bearing pressure again